Swayam Prabha. Digital India. Educated India.
Now, for homogeneous deformation what happens? Since for a straight line A is also a constant, capital A is a constant, I can simplify this expression for lambda A further for homogeneous deformations lambda of A would be square root of C A dot with A integral psi 0 to psi n d psi divided by square root of A dot with A integral psi 0 to psi n d psi. This is 1 since A is a unit vector along a directed line segment. That is, I am looking at straight lines in reference configuration. I am not looking at a curved line in the reference configuration. I am not looking at a circle or ellipse in the reference configuration, I am looking at a straight line in the reference configuration. So, these two will cancel out each other, denominator is 1. So, I will have it as root of C times A dotted with A. I have pulled out this root of C times A dotted with A because A is a constant and C is also a constant, and hence it comes out of the integration. Since I am again looking at straight lines in the reference configuration mapping on to straight lines in the current configuration. Okay. So, this root of C A dotted with A is independent of psi and hence I have pulled it out of the integration. Okay. So, this is the sets ratio along a direction A. Okay. So, now I want to compute C in terms of what was C? C was F transpose F. I want to relate this as a tensor function of capital H. Find this as a tensor function of capital H. Okay. You know that displacement u is small x minus capital X, hence dou u by dou x, which is capital H would be F minus identity tensor, this is nothing but 1 0 0 0 1 0 0 0 1. Basically, if I compute grad of u with this expression, I will get this expression for relating H and F. Okay. So, what is F now? F would be H plus identity tensor. Okay. Now, substituting this back in here, I will get C to be H plus identity tensor transpose multiplied by H plus identity tensor, which will be H transpose H plus H plus H transpose plus identity. Okay. Note this F transpose F is not equal to F square unless F happens to be a symmetric tensor. F in general is not a symmetric tensor, so it is not F square. We will see that there is another quantity called left Cauchy-Green deformation tensor, which is FF transpose. So, FF transpose and F transpose F are not the same, you have to remember that. You have to do the transpose in the appropriate A or B. Okay. Okay. Now, substituting this back into lambda of or further simplifying C, you will find that C can be written as 1 plus 2 epsilon plus H transpose H, where epsilon is 1 of H plus H transpose. What happens is, in many applications, this is a exact equal to, okay. In many applications the order of the components of the H should be of the order of 10 power minus 3, okay. In many applications the order of the components of H would be 10 power minus 3 or lesser. Okay. So, what happens to H transpose when H power order of the components of H is of order 10 power minus 3, H transpose H should be of the order 10 power minus 6, because it is the multiplication of the components of H. Okay. So, H transpose H is matrix multiplication of each of the component of H with respect to itself. Okay. So, what will happen is, this will be of the order, if H is of the order 10 power minus 3, this would be of the order 10 power minus 6. Okay. So, what we do is, we neglect this and compute C approximately as 1 plus 2 epsilon, that is what we approximately compute C as. Okay. Having computed C, let us substitute that in the expression for lambda of A is square root of C times A dot with A, that will be square root of 1 plus 2 epsilon A dot with A, which is an approximate estimate of C, which is an approximate estimate of C. Okay. So, let us expand this further, this will be root of 1 times A dot with A plus 2 times epsilon A dot with A. Okay. Here again it is 1 times this dot with A. What is 1 acted upon by a vector A? This will be A itself. So, 1 A dot with A would be A dot with A. As we know, A is a unit vector, so this will be 1. Okay. So, lambda of A can be written as square root of 1 plus 2 times epsilon of A dotted with A. Okay. Now, you have to remember that 1 time epsilon of A dotted with A is not equal to epsilon A dotted with A. This is not equal, this will be a tensor quantity, whereas this will be a scalar quantity. Okay. Where this will be a tensor quantity, whereas this will be a scalar quantity, because this is a second order tensor acted upon by a vector, gives you a vector dotted with a vector will give you a scalar value. Okay. On the other hand, here A dotted with A will give you a scalar value, and this epsilon is a second order tensor. So, this will be a second order tensor and this will be a scalar, hence the order itself does not match and these are not equal. Okay. So, this is this. Now, this entire thing is a scalar though, this entire thing is a scalar, let us call it as epsilon of A, that entire thing is a scalar, which let us call it as epsilon of A. If the order of H was of the order 10 power minus 3, if H were of order 10 power minus 3, then what will be epsilon? Epsilon components also will be of order 10 power minus 3. Okay. A is a unit vector. So, A would be components of A would be of order 1 or lesser. Okay. So, epsilon of A dotted with A would be of order 10 power minus 3. Okay. Now, I have 1 plus 10 power minus 3 square root, this I can approximate it as 1 plus 10 power minus 3 by 2. From Taylor series expansion, we know that root of 1 plus x is 1 plus x by 2 when expanding about x equal to 0. Okay. Expanding about x equal to 0, that is the Taylor series expansion. This is Taylor series. Okay. So, I use that to write this as 1 plus 2 times epsilon of A divided by 2, which will be 1 plus epsilon of A. Okay. So, what is epsilon of A then? Epsilon of A is, we saw already that epsilon of A is the engineering strain which is lambda of A minus 1, which is change in length by original length okay, of the line segment oriented along A. Okay. So, now what is this? This according to our expression is epsilon times A dotted with A, that is what we substitute epsilon of A as. Okay. So, this is an important equation. What it tells is the change the change in length by original length of a line element oriented along A in the reference configuration. Reference configuration is epsilon of A, which is epsilon A dotted with A. Okay. That is what this tells you. This is like your normal stress, wherein you saw that sigma of n was, compare this with sigma n expression, it is sigma transpose n dotted with n, right. Sigma is a symmetric tensor. So, sigma and sigma transpose it does not matter. So, you can see analogy between them. Okay. You can see analogy between them. Okay. So, this is the normal stress acting on a plane, this is the change in length along a particular direction is given by epsilon of A, which has a similar expressions. Okay.